Asynchronous activity for Tuesday, April 26th. What we're doing today is I'm giving you time to complete your high adventure science astronomy activity, Is There Life in Space? We're working on activity 3, and we will start with page 3. You should have already done pages 1 and 2. Page 3 talks about how the star is moving, and we did take some time to finish this the other day, so hopefully you're done with this part as well. But in order to do this one, it just has you take a look at how the star's spectrum changes as it moves toward and away from an observer. And the question is, can the scientists be certain that their star is not moving? And that was if the scientists observed that the light from a star seems to be yellow in the visible portion of the spectrum. So can they be sure that it's not moving? Okay. We're going to go ahead and go to number 4, and this talks about the importance of angle. And I'm going to go through this very quickly with you so you have time to work. So with this one, it has you perform the challenge to find an angle of orbit that maximizes the motion of a star toward and away from you, and an angle of orbit that prevents you from seeing any motion of the star. And to do that, as I scroll up here, I'm just going to double click on my touchpad. Click on the button, and I can change the angle by dragging. And that's the angle of view. Hopefully you can see that okay. And so if I go ahead and press play, you can see on the graph on the right that this is measuring the velocity of the star relative to us. And so remember, as the planet moves, the star is also moving. So as the planet moves away from us, the star is moving toward us, providing what we'd see as a red shift, so velocity toward us. And as the planet moves toward us, the star is moving away from us, and that wobble is what we measure. Okay. And so once again, you're going to take a look at which of these orbital angles prevents you from seeing the motion, and to see the angle, look down here in the corner. And so you can see as you go from 90 degrees to 0 degrees. And answer the rest of the questions. I'm going to try to make this quick so we can get through it. The absence of wavelengths, when an astronomer sees that there is no velocity shift, can they rightly conclude that the star does not have planets? Okay, I'll go to the next one. Go ahead and answer those questions. The importance of mass. And so how does the mass of a planet affect the wobble of the star? And the challenge is to set up a model with a very large, very heavy planet that results in a similar velocity graph to this one. Now, this one's kind of tricky. Spend a little time on it. If you get frustrated, it's not going to be a big deal. So I'm going to go ahead and let me go ahead and increase the mass. I'm just going to increase it to very heavy mass, about halfway, and then press play. And you can certainly see the wobble, but that wobble isn't being detected from the observer, us, assuming we're on Earth, because the tilt is at 90 degrees to us. As I tilt this, then you can see how the wobble changes, correct? All right, you can see that. And the greater the tilt, go to the extreme, the greater the amount of velocity that the star is making because of the planet's orbit. Okay, so your job is to try to use a massive planet and try to replicate, I'll go ahead and clear the graph, and try to replicate this graph here. And it goes, here's 0.2 meters negative. That means it's going toward the observer, and 0.2 meters in the positive is going away. So it's a very small movement. You're going to use the zoom button. I don't think this is really user friendly, but I'll show you what they mean. I'm going to go ahead and let me change this to just maybe barely an angle, and I'll press play. And then you can see that it's moving. If I click zoom, how much is it moving? Now I would want a movement somewhere between 0.2 meters and negative 0.2. And I'm doing that. And this would work for it. You can see how the graph is really zoomed in. I don't like that you don't have control over the extent of the y-axis here. But it's supposed to be between 0.2 and negative 0.2. Well, 0.04 and negative 0.04 and 0.04 is certainly between there. So this certainly would work. You're looking to try to replicate that graph. Okay, take a snapshot, answer the questions, go to number 7. The noise part, you can see with a perfect telescope, and then what it might look like with what's called noise. You'll remember that from the Genius by Stephen Hawking, Are We Alone? When they were shouting into the auditorium and they were trying to detect the alien. So we take a look at this. So noise is like background information that the telescope is picking up. And could you say that this is showing a planet revolving around a star? Click one, answer it, go to the next. And now you're going to take a look at creating your own noise. It says position the orbit angle so that it's close to but not exactly 90 degrees. So, maybe 86.65 I picked. Make a planet that you can just detect. So I'm going to go ahead and create a planet here. I'll make it bigger and we press play. I'm going to look to see if this shows just a little bit of movement. Maybe I want a little less movement than that. Barely detect, it said. So I'm just playing around with the parameters here. Can I get a planet that you can barely detect? I can't really see that graph moving. I think this one is the one that says not to use the zoom. Yeah, without using the zoom button. So this is pretty good. I can see it barely go above the line and barely go below. Okay, and then it says set the telescope to perfect. That's what it's at by default. And then change the precision to explore how varying the level of noise affects your ability to detect the planet, and change the orbital angle to see how a combination of orbital angle and telescope precision affects scientists' ability. So what is that saying? First of all, let's talk about noise. Decreasing the telescope's precision is going to increase the amount of noise. So if I always say kind of go to the extremes to kind of get the relationships between things. It makes it a little bit easier. So if you take it all the way down to the lowest, which is 5%, you can see how the graph makes it more difficult to see any movement of the planet around, or any movement of the star caused by the planet. Okay, I'm going to go ahead and increase the angle, and you can see what effect that has. And you can assume, right, that when you increase the angle or decrease the angle, change the angle, closer to 0 gives you the easiest way to detect a planet because you're seeing the most motion in relation to Earth, the observer, the telescope, compared to when it's at 90 degrees, when you would actually see 0 movement toward or away from the telescope. I hope that makes sense. Okay, answer the questions. Last page. Now it gives you an example here. It says finding planets through the noise using mass. Set the telescope to 100. That's default. Make a planet with a small mass. Select the angle that allows you to detect the planet, and then set the precision of the telescope to explore how varying levels of noise affects your ability to detect a planet. So same thing, you're going to make a planet with a small mass. It's already got a pretty small mass here as the Earth. You can certainly just keep that one and answer the questions. Okay, that is your lesson for today. I will go ahead and sign off here and let you complete activity 3. And remember that activity 4 we will do on Thursday. Tomorrow we're going to do another simulation activity similar to this one. Activity 4 on Thursday, and then we'll have our quiz on Friday before we begin our last kind of mini unit here on learning about the Big Bang and life cycle of stars. All right, hopefully you don't have any questions, and enjoy the rest of your day.